Good afternoon, everyone, and thank you for joining NearMap's instructional class. Today, my colleague Connor Tluck and myself will be going over how to gain advantage in planning and design with high-resolution geospatial content using our own NearMap data. To briefly introduce NearMap, we are an aerial imagery and geospatial content provider capturing current high-resolution imagery published to the cloud within weeks. We currently capture 80% of the U.S. population and started U.S. capture in 2014. We capture using fixed-wing aircraft attached with our patented camera system in Class E airspace to acquire the high-resolution imagery with 2.2-inch ground sampling distance. We also provide a number of derived products off of our captures in the form of 3D content and ground feature recognition data generated through machine learning. Our content stack consists of vertical top-down imagery, panorama multi-perspective imagery, oblique perspective imagery that is measurable, as well as 3D and vectorized AI data layers. For a deeper dive into our 3D, we offer textured mesh, point cloud, DSM, DEM, and true ortho models. Today, Connor and I will be highlighting how this data can optimize your design workflows and engineering base maps as we derive contours in Civil 3D and InfraWorks. All right, so as everyone can see, I have my Civil 3D window open here, and next I'm going to be loading in all of the NearMap content into here to show how it kind of looks in this environment, as well as generate contours off of our DEM. The first thing that we're going to want to make sure that we do is have our drawing set to the correct coordinate system, and this is going to make sure that everything is coming in the right place. And if I did have some outside line work existing, that everything is kind of, working together in the correct environment. So the example today is going to be of Boulder, Colorado. So we will be using the state plane north zone feet for Colorado. Okay, great. Now that we have our drawing space defined, then we're ready to bring in some of our content. The first piece that we are going to import is our backdrop vertical image that will line up with all of the other layers. For GeoTIFF, we're going to be using the map insert command. As you can see here, it will be reading the JGW file associated. We just want to make sure that we are in feet as our coordinate system was defined as. And zoom to our image. Great. So as you can see now, we have our backdrop image loaded in. This will be kind of the base background for all of the other content that we're going to start loading in now. So next we'll be bringing in our AI shape files with the map import command. Map import will allow a conversion of the shapefile into Autodesk feature layers. As you will see in a moment, this will bring in everything as a working layer that you can interact with as you would any other line work in CAD. All right, as you can see now, I have loaded in our AI vectorized layers and adjusted the symbology accordingly. The layers I've decided to bring in are asphalt, medium-high vegetation, and lawn grass. I am going to bring in building characteristics as well with the building outlines, but I did want to show that separately to kind of show just a rundown of how the attributes might be imported along with it. So similar to our other output windows, we are going to actually select data within here. What this is going to do is tell the import to bring in those attributes as they exist in the table in an Esri environment, so that the way that they are going to be legible in the properties in Civil 3D as well. We're going to want to create object data and then select the fields that we would like. So I think for this example, we're going to, let's say, pull building heights. And since the buildings are polygons, we're going to want to make sure that we import them as closed polylines. Great. So you can see our buildings are now loaded in here. And then if I wanted to click on one and go to the properties, we have some other data kind of displayed in here as well. So we have the building height, as well as the capture date for this and some other information. So a great thing about this vectorized AI is that it is a great tool for just some preliminary design drawing. A lot of time can be spent just drawing out certain features in the real world by hand. And then using this, which is coming off of our camera system, it's just a great fast tool just to have it ready for any exhibiting and preliminary design. You're not going to be spending the time drawing out these lawns and these roads and all the different vegetation information. So let's take this example one step further and bring in a 3D DEM underneath here and generate contours, because that's going to be a great tool for considering any type of site planning and design. So I'm going to be connecting the raster in here of our DEM solely for display purposes, just to show everyone what the DEM will look like. For generating the contours and creating the surface itself, we're actually going to use a different tool, which I will explain in a moment why we're going to do that. Okay, perfect. Now we can see here the DEM is loaded in, and visually this is telling us a lot about the different elevation characteristics going on in this area. You can see clearly where there are certain hills and slopes and where it becomes more mountainous versus the neighborhood. Okay, so now we're going to be bringing in our DEM a little bit differently and creating a surface shell in Civil 3D. This will allow for us to start generating our contours. So we'll want to go to surfaces, create a surface. We're going to name our surface. And then here is where we're going to select the parameters for our contours. I am going to change it to 5 and 25 foot for the background, just so that it's spaced a little differently. And we are creating a tin that we will be generating the contours off of. This, I think, is the most optimal way in Civil 3D for contour generation, because it is telling, kind of our drawing space here, how to consider interpolating points between contours from the 3D rather than just a 2D input. So although we visually can't see anything that has been created in here, we do actually have a shell now of our surface that is ready to have our DEM loaded on to generate those contours off of. So we'll want to add our DEM. And now that tool is going to take a minute to run as it is processing the contours and interpolating points between the surface from that DEM. Okay, so now that our surface tool has finished processing, you can see the contours that have been generated within here. I decided to turn off the backdrop image just for speed processing times for the purpose of this presentation. As you can see, our contours are now visible. They are giving that, 2D representation of the 3D space from our DEM. You can see where the different elevation changes occur. What we have right here is the tin model. As you can see when I go to the properties, this would be a great input for the slope toolbox within here. If you wanted to do a profile on slope or grading, the tin would be what you would want to input for that. But for the purpose of a lot of just preliminary design and planning and just, being able to click around, we're actually going to explode the surface twice. The first explosion, we'll just put it as a block reference, which may be preferable to some CAD users, but I'm going to go ahead and explode it a second time. Okay, so now that it is exploded again, you can see each contour is now able to be selected kind of as its own line. And let's just zoom in here and make sure our elevations look good. All right, so checking our elevation, we have this contour here selected. This is Boulder, Colorado, so a higher elevation city, and it's showing 5,755 feet, which sounds about right if you know Boulder. So what can we do with all of this information for the AEC space is the great question to ask. And that's a lot of preliminary design and exhibiting. This makes it a lot faster and easier just for some initial drawings to get marked up and put together. If you just wanted to quickly show certain areas and what types of content are in there without having to go out and survey or hand draw off of other existing aerials, this could be a really great tool. For the contours themselves, I mean, having elevation data, I think, is the basis for pretty much any initial civil engineering planning, for knowing profiling, grading, slope friction. If you had a lithological data set in here, you would be able to do slope friction calculations for these roads, cross sections, and then cut and fill analyses as well in the preliminary design part of the process, at least doing some cost analyses, and just site design in general. If you wanted to, get some takeoffs for area, saying, we need to demo a block of buildings. What's the total square area that we're going to lose on that in terms of vegetation inventories? If there are environmental organizations involved in your project, if you need to, be relaying what types of vegetation removal the project is going to be undergoing, you don't need to send people out to survey and collect all of that information from just the AI. You'll be able to get a good enough start and rough estimate for those calculations. I am now going to be passing it off to Connor, who is going to load the content stack into InfraWorks and show the planning and design possibilities in InfraWorks. Thank you.
Hi everyone, my name is Connor Tullock and I'm a solutions engineer here at Nearmap. Today I'm going to be loading up a full Nearmap content stack within the InfraWorks environment. So that's going to be high resolution imagery, 3D terrain data, and then vector AI content. Once our data is loaded up, we're also going to look into concept planning, workflow, material takeoffs, and quantity estimates, as well as a 3D rendering workflow as well. So the first step to do this, we need to load up a new InfraWorks workspace, which I have here. I've named mine Boulder, since that's where our sample data set is coming from. And then we need to select our coordinate system as well, and then just give our model a minute to load up. Okay, so our InfraWorks environment has now been established and we're ready to load up our Nearmap data. Before we get into that, let's run through each content type and how Nearmap produces that data set individually. So the first piece of data is actually a derivative product. This is our terrain data set, our digital elevation model. And we generate this after each flight by using photogrammetry techniques to establish 3D terrain information off of our source photos. This is going to help us establish that 3D base map. And then after that, we're going to overlay our high resolution 2.2 inch ground sampling distance data on top of it. That's going to give you your actual visual photo overlay on top of the terrain. The final data set that we're going to load is our vector AI. This is probably our most exciting content type that we have at the moment. And what we do here is we have a machine learning model that assists with ground feature recognition. And then we vectorize that content. And the reason that the vectorization is so important is because different programs like CAD and GIS software platforms can very easily then understand this information and load it into the digital world. So in the case of InfraWorks, this vector data is going to be loaded in a shapefile format, and it's going to help us directly create a lot of these really interesting InfraWorks 3D objects like buildings, trees, different ground cover types, roads, things like that. Okay, so let's get started by loading that 3D content up. So we want to go to our data connections and select raster, and then navigate over to our digital elevation model. This is going to be in a TIFF format. And then once we've established that data connection, we want to configure that data into a terrain as a type. And then close and refresh and give our model just a minute to load up here. Okay, so our elevation model has now loaded, and what we're looking at here is the triangulated surface of the existing terrain in our area of interest here. So you can see underlying boulder overshadowed by this mountain range in the distance there. So in order to gain the extra level of understanding of the area that we're looking at here, the next piece of content we need to load is a high resolution base map. So we load this very similarly. We go to our data sources and then establish a new raster connection here. And we want to load that as ground imagery this time instead of a terrain model. We're going to close and refresh that and give it a minute to just load all of that content and overlay it onto our terrain. Okay, so after just a few minutes, our high resolution image has now been draped over our terrain model that we previously loaded. If we just zoom in here, you can see how extremely high fidelity Nearmap's vertical imagery really is. We provide it at a 2.2 inch ground sampling distance resolution. Really lets you get the full context of what is going on in your site rather than just seeing that 3D data. If we go over here to this area of a little bit more of an elevation difference, you can really see how tight that triangulation is. You can see that the road has been clearly defined. You have the side slopes down that hill very clearly defined. And then looking at this wireframe, you can see the spacing between the different data points is extremely tight, giving you a very high degree of accuracy on your area that you're looking at. Okay, so this is our workspace as it stands now. We have our high resolution image draped on top of our terrain data, and next we're going to load our most exciting content type, our vector AI data. The reason that this is so exciting and has the potential to be such a massive game changer is because it's the next evolution in mapping and understanding and digitizing the world, right? The starting step of high resolution vertical imagery is great. You can visually understand your environment and recognize what's going on in current conditions. Adding terrain data gives that third level, that 3D aspect to gain an additional level of understanding. And the vector AI takes that process that a human being does with their eyes and will process the imagery, automatically create points, lines, and polygons for common ground features that our clients may have value in. And this lets us very easily digitize that content and bring it into platforms like CAD and GIS, and we're going to demonstrate that here today in the InfraWorks environment. So the first object that I'm going to use is our roads layer, right? So we recognize this as asphalt and concrete. What I've done is I've done a little bit of post-processing. So our algorithm identifies edge of pavement, but I've gone ahead and done a little bit of scripting to identify the road center lines, and then we're going to digitize those by creating road layers in InfraWorks. So we load this content up by going to our directory here and loading a shapefile that identifies those road center lines. We want to make sure we load that content as the road InfraWorks layer, and then we want to select a style that fits with the environment that we already know what that road is going to look like. So here I just have a basic asphalt layer. And then we're going to drape that onto our existing terrain. Since these are existing roads, we want it to match the profile of the ground data that we've already loaded. All right, so after just a few minutes, our shapefile center lines have been converted into InfraWorks road objects. So these have loaded as planning roads on this asphalt default style that we selected. And as you can see, when we select it, we have a number of attributes that are built in. This is some of that utility that InfraWorks can offer where it can help to automate a lot of the design process, loading design standards, making, assisting the engineer to make design decisions. So these are just existing roads. We're going to talk a little bit about how proposed roads work and how those can be created using the Nearmap content stack. But first, what we want to do in this particular case is convert these planning roads into component roads. A little bit of a workaround here is to use the traffic simulation tool. Again, really great tool to do those traffic analytics on existing and proposed roadways. And what it's going to do is, in order for that additional functionality to get built into the roads themselves, to run these traffic simulations, it is going to automatically ask you if you want to convert these planning roads into component roads. And that will give you profile access, horizontal constraint access, and a number of other quantity estimate items as well. So we're going to run this traffic simulation to convert all of the component roads. Again, keep in mind that there's a whole deep rabbit hole of traffic analysis that you can go down. We're not going to touch on that today. We're just going to use the utility of this conversion tool to get us over to our component roads for now. So all of our roads have now been converted. We have component roads for our entire existing road network here. If we click and select one of the segments, we can see that we have horizontal alignment information being displayed, our beginnings and ends of curves. And then we also have the ability to go into our profile viewer and see what the road profile is doing in that Y direction. So here it's really an approximation. It's simply draping on top of the existing terrain, but it can give you a good understanding of what sort of grades we're dealing with. And again, it's piggybacking on that accuracy of our 3D terrain model. There's a lot of utility built in here with some of these road tools. We're going to talk about quantity estimates and removal items and earth excavation at the very end of the video, but now we're going to just continue on loading up our AI data set and digitizing the city of Boulder here. So let's go into our shapefile and load up our next AI content here. So we're going to select our building layer next, our 3D buildings. So selecting that shapefile, we're then going to configure that vector file that we've loaded. And we're going to select the InfraWorks building object type. We're going to have a little bit of option input here for heights of building, extrusion, different style options. We're going to go with a random colorization option. Something to remember, these buildings can actually get highly accurate if we pair it with our other 3D types, such as our digital surface model, which will very accurately define roof heights. But for now, for this use case, we're just going to simply do extrusions, and that'll be good enough for us in this instance. Okay, so our 3D buildings have now loaded. Again, what we've done here is we've loaded our the Nearmap AI vector building footprint layer as a shapefile. This has defined the geometry in the plan view of all of these buildings, and then we have simply loaded them as building objects and extruded up from those building footprints that we've loaded. So this is giving a impression of the real world. It's not quite the perfect representation of these buildings, but it's going to get us pretty close. Again, we have much more accurate LOD2 building workflows that we've posted on our documentation that I also can link after the video. The digital surface model that we provide can help to very accurately model tops of buildings in addition to those building footprints and get much closer into the real representation of the world. For this use case, though, this is going to be fine for us. It should just load that rendering of Boulder itself. We're also going to just go ahead and continue to move along here and load up a number of additional AI vector layers. The next one we're going to load is our tree layer, our medium vegetation layer. So this is defining all of the edges of these medium tree canopy, the limits of the canopy of medium trees. So what we're going to do here is a little bit of a different workflow where we take our shapefile and then we use some of the functionality of InfraWorks itself in this table setting to randomly distribute 3D tree models within the canopy layer and give that representation of what the trees are probably doing in those areas, more or less. And it's going to really create a high quality rendering for us. So we're going to select our tree model that we want. I know that this is a pretty decent one. I've used it a number of times as well. Confirm our geolocation. We're going to drape the object on top of our terrain. And again, we're going to use this table setting for object spacing and object spacing variance to distribute these tree models within our workspace. So we're just going to give this a second to load up, and then we'll jump right back in. All right, so as you can see, we have 3D tree objects now that have been distributed among our canopy envelopes, and this adds a nice extra piece of depth to our model. We have a lot of AI attributes. What I'm going to do is I want to avoid going through the loading process for each one. I'm going to do one additional one for a concrete slab ground layer. This is a coverage area. It's a pretty typical type of InfraWorks object that you load up, but there are a lot. We have things like power poles, power lines, solar panels, different roof attributes in terms of damage. We have cars, again, different types of ground coverage. All of these can be loaded. As long as it's vectorized content, it can be loaded within the InfraWorks environment. So let me jump ahead here to concrete slab. What we want to do is select that shape object. We want to move over to our configuration options and select the option for coverage area, and then select a good rule style for something that's going to represent that object well. So I think there's actually a direct concrete terrain type, so we're going to go with that one and then hit load and give it a second. Moving over to this aerial view, we can see that our concrete slab has been identified at the ground. We now have an InfraWorks object associated with it. We have our sidewalks. A lot of our driveways have been identified by the algorithm as being this material type. Again, adding that extra additional layer. All right, so that was just a handful of AI attributes that can be loaded as 3D objects within InfraWorks. Again, we have many, many more, and what I'm going to do is go ahead and go through that exercise here to load them on my own off camera, and we'll come back and show what the full 3D rendered boulder scene looks like using only near map content, our high resolution imagery, our terrain data, and then that vector AI data to load up these InfraWorks 3D objects. After that, we're going to talk about a little bit more of the engineering side of this. How do we apply a lot of this content stack to more of a concept planning rather than a simple 3D rendering environment, looking at things like quantity takeoffs and earthwork analysis as well. So now I'm going to jump into that completed 3D rendering video and then move right on to concept level planning after that. Alright, so I hope everyone enjoyed that completed 3D rendering of Boulder, Colorado, and can hopefully see some of the utility that the full near map content stack has when trying to create some of these 3D rendered environments of the existing world. To conclude here, I want to talk a little bit more on concept planning and development, a little bit more of the engineering side of things here. So I have another site loaded in Durham, North Carolina of a subdevelopment. And I have the same data stack loaded. I have our high resolution imagery, our terrain data, and our AI data to create 3D objects in the world here. And I've drawn a new proposed road, a little bit in a goofy place, but just to demonstrate some of the utility here. As you can see, we create this component level road. We can see the profile view which is going to be a draped elevation. Again, you have that ability to adjust that profile as you see fit as the engineer. And out of the box, InfraWorks is going to apply a certain level of design standards that you as the engineer has established. You also have access to the cross-section viewer, so you can set the super elevation on your proposed roadway all along the entire length of it. As you cycle through stations, you can fine-tune, adjust that. But again, it is already out of the box going to try to satisfy design standards that are associated with that component road. So using the earthwork quantity calculator in the bottom right here, we also have the ability to get a cost estimate on how much earth is required to move in order to construct our road, which is very useful. And we also have a material quantity estimate calculator. The reason that this is so important is because it can really help to bridge the gap between the value of these vector AI components once they've been introduced into the InfraWorks workspace. You can see that in the 3D model layer here, anytime that an AI attribute that we have created, has been imported from Nearmap, is being intersected with the new proposed roadway, it's going to be reflected in that material takeoff estimate. So it's going to help identify ground features that are intersecting and interfering with any new proposed design. So that's things like vegetation, interference with existing utilities, which types of ground features, like if you're already hitting existing concrete or asphalt, what sort of costs need to be reflected when bidding that job. InfraWorks also offers the ability to generate a CSV report from this, which makes it very easy to share amongst other contractors, engineers, and clients as well when generating these cost estimate and bids. So that's going to conclude Nearmap's lesson at Autodesk University. Hopefully everyone found it informative and learned a little bit more on how to best integrate Nearmap's content stack in both Civil 3D and InfraWorks. Enjoy the rest of the conference, and thank you so much for attending.